In today's note, we are going to look at going from words or scenarios to rules. Before we get into that again, we're just going to do a little bit of review, looking at some multiple choice questions, similar to what you may find on EQAO. So again, one, to kind of get you used to those types of questions, and two, to just kind of review the concepts that we've looked at. So the first one, or 9, which table of values shows a linear relation between C and N? So keep in mind what we've talked about before. A linear relation has a rule or a pattern of y equals mx plus b. In this case, because we're using C and N based on the way they've been entered into the tables, we can rewrite this as C equals mn plus b. Right? So what we're looking for in a linear relationship, because that's the key term there, is it increasing by the same amount? So if I look at A, and it's just going to be kind of a process of elimination. Remember, we have our x and our y, and we're looking at how does the change in y over the change in x. So if I look at the first one, if I see it's going up by 2, but then up by 4, the x values or the n values are all increasing by the same amount. So in this case, I have an odd one out here because this one is increasing by 4 when the others have been increasing by 2. So this one does not work. For C, again, I'm going to go through up by 4, up by 7, up by 4. The n values or the x values are all going by the same, but because I have that inconsistency with that second one, C does not work either because they all need to be increasing by the same amount. B, again, I can see that the n values or the x values are all increasing by 1, which is good. And the C values, so 1, 3, 5. So here, all of them are off. Right? They're all different. So again, B can't be the same because again, it needs to be increasing by that constant amount, or that m value or that multiplier needs to be one number. So by process of elimination, that leaves us with D. So we know it has to be correct, but if not, let's just double check. Anyways, we can see the n value is increasing by 1. The C value is increasing by 3, so that means D is our linear table. For 10, which relation does not have an initial value of 50? So the key thing here is the initial value of 50, and the question asks does not. So you may see some questions like that where they throw in kind of that negative there. So you're looking for something that does not have this. So make sure you read the question carefully. Remember, the initial value is the b value. So if I have an equation, it should be y equals mx plus b. And in terms of our question, we need it to be y equals anything x plus 50. So that's what we're looking for. And we're looking for all the odd ones, or all the ones that do not have that initial value of 50. So if I look at A, I see I have a constant, or it's just y equals 50, or a constant of 50. So that one is good, because again, remember, if it was not an initial value or not a constant, it would be paired up with the x. B is written backwards, but I can rearrange it. But I can see that I have that constant of 50, so that also works. C has a 50, but with the x value, so that one doesn't work. So that one does not have an initial value of 50. And C again has a constant of 50 in front, so that one does work. So based on the question, because I'm looking for which one does not have an initial value, that means C is my correct answer. So just in case you're reading it and you're like, why is it an X? So C is correct. It does not have B equals 50. So again, the check marks and the X's are there just to see, does it have the initial value of 50? If so, that means I cross it off my list. Actually, let me just change that. So to fill in the question, does not, so this does not, or that does have an initial value of 50, so that can't be it. That one does, and that is my correct answer because it does not have an initial value of 50. That way, if you're just going back and looking at it, there is no confusion, hopefully. So we're going to look at some words to rules, and we're going to be looking at it in some real life situations or just some scenarios, so you can kind of get an idea of how to turn or how to go from words to tables or words to rules. So in example 1, the senior girls volleyball team held a car wash to raise money for new uniforms. They charge $10 for each car that they wash. The first thing we want to do is write a dependency statement and determine the independent and dependent variables. So what we need to do is we need to look at the money compared to the number of cars washed. And we need to figure out which one depends on the other. Well, in this case, the money, or money earned, money raised, depends on the number of cars washed. And this is important because this is going to help us figure out our X and Y values. So the independent variable, the one that does not depend on the other, would be the number of cars. And the dependent variable, the one that depends on the other, in this case, is money. So if we looked at the rest of the question, we can see that based on the graph, the money raised is the dependent because it's Y, and the X is the independent, the number of cars washed, and we can also get that from our table. So we want to create a table of values to help us and then graph this. So number of cars washed, if I wash 0 cars, I get 0 money. If I wash 1 car, if I go back up to the question, it's $10 per car, so 1 car means $10 raised. 2 cars means 20. 3 cars mean 30. 4 cars mean 40. And I can then plot this on my graph. So 0 cars, 0 money. 1 car, 10. 2, 20, 30, 40. And I can continue this if I want. If I wanted to. I can go through and continue that. So should you connect the points on the graph, why or why not? So should we draw a straight line through this graph? Based on the scenario that we're looking at, no, we should not. And the reason is because it doesn't make sense to consider decimal values. So it doesn't make sense to consider decimal values in the number of cars you wash. Because we're never going to wash half a car or a third of a car. It's always going to be 1 car. And this type of data is called discrete. So discrete would just mean basically it's fixed. So there's no difference in between. It's just set numbers. So 1, 2, 3, 4, 5, 6. There's nothing in between. It's the fixed number. Is this an example of a direction or partial variation, or direct or partial variation? And this would be an example of, so let me erase that. This would be an example of direct variation, and the reason is because the initial value is 0. So again, go back to the previous notes if you have trouble distinguishing the two, but the initial value is 0. You could also look at the graph and see that it goes through the origin. That's another way to tell as well. So the initial value, or the constant, or the y-intercept is 0. So we need to describe this relationship now with an equation or with the rule. So we know it has to be in the form y equals mx plus b. So I'm going to start with my y. To figure out my m, I need to go back to my graph or my table to help me figure out what is my multiplier, or what am I increasing by. And if I look at my table, I can see that the m's are increasing by 10 every time. The x values are increasing by 1. So that means my m value has to be 10. Another way we could have gotten this is if I go back up to the question, where have I seen this before? And if I look at the question, it said $10 for each car, or $10 per one car. So $10 per one car is my multiplier as well. So there is a way to get it by looking at the question as well. So my x value, I don't have a b value. I could throw in plus 0 if I wanted to. Let me actually keep it color coordinated. Plus 0, because if we go to our graph and look at the y-intercept, where does the line cross? Well, it crosses right there. So my equation is y equals 10x plus 0, or I could just say y equals 10x. Or if I wanted to make sure that I use the variables that the question gave me, it would be m equals 10 times c, or sorry, not c, n. Or money earned is equal to 10 times the number of cars. In example 2, the math club decided to order Mathlete t-shirts. The company that makes the t-shirts charges a flat fee of $50 to set up the printing machine, and then $50 per shirt. So key things here: flat fee of $50, and then $5 per shirt. So based on the last example, $5 per one shirt. So that might be helpful in the end. So $5 per one shirt. If we want to write a dependency statement to help us figure out how these two variables relate, right? So again, looking at what we're our scenario, the cost depends on the number of shirts. So again, you kind of look at the two things that we're looking at. So in this case, it'd be cost, or money, and shirts. So the cost in this case depends on the number of shirts. So our independent variable, the one that does not depend on the other, is number of shirts. And the dependent variable in this case would be the cost. So we want to now take this and come up with a table of values. So the number of shirts, here you're putting it into increments of 5 or 10. So we're going to have to use a little bit of math to help us figure out this table. It's not going to be as easy as just plugging it in. So the first one, if the cost is 0, or the number of shirts is 0, what is the cost? If we go back up to our question, we had a flat fee of $50. So that means even if I buy 0 shirts, it's still going to cost me $50. So I do need to have that in there as well. Now, for 5 shirts, I need to figure out what's it going to cost me. So off to the side, if you want, 5 shirts times $5 equals 25. So that means $25 for 5 shirts plus my initial cost will be 75. 10 shirts, so I'm adding 5 more, so that's going to be another $25 on top, so it'll be 100. 15 or another 5 shirts, so 125, then 150. So we have our table of values. We can go and plug this into our equation now. So we know at 0, or number of shirts, it's $50 regardless. At 5, it's 75, so I'm going to roughly estimate here. 10, it's 100, 15, it's 125, and 20, it's 150. If I wanted to keep going, I could see that every time I add 5 more shirts, it's going to add or cost me $25 more. So at 25, it'd be 175, 200, 225, 250, and so on, if I wanted to keep on going. Should you connect the points on the graph? Why or why not? Again, I'm going to say no, because you can only order whole number of shirts. So you can only order whole number values of shirts. So similar to the last example where you could only order or you can only wash whole number of cars, you're not going to wash half a car or a third of a car. The same thing with this question. I'm not going to be able to order half a shirt or whatnot. But that does mean, because on my graph my skill only goes up by 5, that does mean that I could have 5 points or points in between each main point that I have because of those whole numbers. So 1, 2, 3, 4, or 6, 7, 8, 9, 11, 12, 13, 14, and so on. Those points would be in there as well. Even though we don't see them, they do exist there. But I'm not going to connect the points with a straight line. I could add in extra small points if I wanted to. Is this an example of direct or partial variation? This is an example of partial variation. And how do we know? And we know because we have a startup fee, or an initial fee, or you could see that we have a y-intercept that is not 0. So describe this relationship using an equation. So again, whenever we have to describe using an equation, we're going to use mx plus b. So I need to find my m and my b value. My m value I can get from my table. So if I look at the table and check to see what it's increasing by, it's increasing by 25 each time. But I also have to look at the x value, and that's increasing by 5 every time. So if I wanted to calculate my m is going to be 25, or the change in y, over the change in x, which is 5, and this breaks down to just 5. So I know in my equation it would be y equals 5x, and then plus whatever my b value is. If I go back to my table or my graph, I can see that my b value when x equals 0, or my graph where it crosses the y-axis, I can see that is 50. So my b value is 50. If I want to put it into terms of the actual equation, the actual scenario, I could say the cost is equal to 5 times the number of shirts plus 50. And again, if we go back to the scenario and check to see where can I see these numbers, we can already see that we have a flat value of 50 mentioned, and we have the $5 per shirt. So we already have stuff in the scenario that can help us get right to the equation. So in example 3, Pearl works at the Grimsby Square selling Christmas cake during the month of December. She is paid a fixed amount of $50 per day plus $2 for each cake she sells. So right off the bat, if we've kind of seen the pattern in the last ones, there are some things that we can highlight here. So we can highlight a fixed amount of $50 per day, and then plus $2 for each Christmas cake that she sells. So we see the term fixed amount, and we've kind of seen that in common before, of a fixed amount referring to our B value. And we have here plus something else, which is $2 for each cake she sells, or $2 per one cake. So I'm going to leave that right there and highlight that, and we'll come back to that later. So we want to write a dependency statement and determine the independent and dependent variables. So again, the things that we're looking at is her earnings, and number of cakes. So which one of those two things depends on each other? Well, her earnings, or her salary slash earnings, depends on number of cakes. So that means the independent variable is number of cakes, and dependent is her daily salary. And we can use now our table of values to help us figure out our graph. So again, if we're looking at a table, remember x and y. So the y value depends on the x, which is the same thing that we've been doing in the first part with that dependency statement. So if we look at the number of Christmas cakes sold based on the scenario, if she sells 0, she's still getting a daily salary of $50 because they pay her that fixed amount. Now, if she sells 5 cakes, what's her salary? Well, again, we can do some quick math off to the side if we want. So 5 cakes times $2 equals 10. So that means if she sold 5 cakes, she would earn $10. So we're going to plus $10. And as we go up, that's 60. So if we're going from 0 to 5, we're increasing 5 cakes. From 5 to 10, we're increasing 5 cakes. So that means we increase the salary by another $10. Here it gets a little complicated because now we're increasing by 15 cakes. So because we're increasing by 15 cakes, that's going to change up our slope, or our increase of the second column. So I'm not going to increase by 10. I'm going to increase by, and if we want to do some math off to the side, 15 times $2, 15 cakes times $2 each equals 30. So that means I'm actually let me color code this. I'm actually going to increase the next one by 30. So that means it's going to be $100. And then for the last one, we're increasing by 25 cakes. So that's going to change how much I increase by. So 25 cakes times $2 is equal to 50. So I'm going to increase by 50 here. So my number of my salary becomes $150. Now you may get maybe thinking about, well, why does this work when I'm increasing by different amounts, when in the example above, or one of the multiple choices, we didn't increase by the same amount and we said that was wrong? Because it's increasing in proportion to that same overall, right? Because we're increasing by 15, so we change what we're increasing by over here. These aren't increasing by the same amount, so it's okay as long as we're increasing in proportion. And it all breaks down or goes back to that $2 for every one cake. So we're showing the different values, but we're still increasing it by the same amount. We're not changing how much it's increasing by, we're just showing different points along this graph. So if I wanted to plot this graph, at 0, there are 50 cakes, or $50. At 5 cakes, there are 60. At 10, there are 70. At 25 cakes, there are 100. And at 50 cakes, so at the very end, there's 150. So those are roughly the amounts. If I wanted to as well, I could go through and continue to go up by tens for every 5. So 15 then would be 80, 20 would be 90, the 25 is at 100, so I already have that. So this is another way you could fill in this table. We still increase by 10 every amount, and we still get those same values. So they're still in par over the graph, we just skipped a few. So should you connect the points, why or why not? Well, going back to our last examples, it's discrete, which basically means it's fixed numbers, so you do not sell decimal values of cake. So no one's going to come by and ask for half a cake or a third of cake in this scenario. Is this an example of direct or partial variation? In this case, it is partial variation. How do we know? The initial value is not 0. So again, we can see that it's not 0, it's higher up. It doesn't start on the origin. Use the graph to determine Pearl's salary if she sells 35 cakes. So we've already looked or plotted this out, but if I want to figure that out, so 35 cakes, so I'm going to go across the bottom, find out where 35 cakes is. Let me use a different color. 35 cakes, and I'm just basically going to go up until I find that point, and then I'm going to go across and find out where it matches up. So in this case, $120 is her salary if she sells 35 cakes. What is this process called? Interpolation or extrapolation. We will cover this a little bit later, but this is considered interpolation because it's inside the data values that we have. So our data values range from 0 cakes to 50 cakes based on our table of values. So anything in between 0 and 50 cakes, we can use interpolation to figure that out. For F, use this to determine how many cakes she must sell to earn $110. So again, I'm going to do the opposite. I'm going to go over to my daily salary, find out where 110 is, go over till I find a point, and then go down to find the number of cakes. So in this case, 30 cakes must be sold. Is this interpolation or extrapolation? Interpolation again because it's inside the range of values that we have. So it's in between 0 and 50 cakes. Use this relation or describe this relation using a equation. So again, same thing that we've done in the past, y equals mx plus b. I'm going to convert this. So my m value, different ways you can figure this out, right? You could have, if you look at the change in values, you could have 10 over 5 was one of them. You could have, we had 30 over 15. Or you could have, another example we had was 50 over 25. Right? So all examples based on what we've looked at or from our table. But the thing it always comes back down to, regardless of which equation or which example or which points we use, it all comes back to 2 over 1, which we get from the original scenario where they talk about it's $2 per one cake. So regardless of what we do, it still all comes back to that original sentence in the scenario, 2 over 1, or 2. So y equals 2x plus, and then our b value. Again, our b value we can get from multiple spots, the table of values, or the graph. So 50 is my flat fee. And again, we could also get that straight from the scenario at the top because it's mentioned the initial or flat fee. If I want to put this into terms or variables of what we've dealt with in this question, the salary is equal to 2 times the number of cakes plus 50. So again, same kind of examples that we've been looking at. The only difference here is now we've added in scenarios. So hopefully we can see the connection between the m value or the multiplier and the scenario. It always seems to be coming back to something per one of something. So $2 per one cake, $10 per one car, $5 per one shirt. So it all comes back to that. And then the b value or the constant or the y-intercept is that initial fee, that starting fee, that fixed amount, right? So just different terminology and just different examples of how we can see it in the actual equation. So hopefully now you can, based on a given scenario, you can come up with the equation or the rule for the scenario, or at least have enough to work through it where you can come up with a table and then come up with a graph to help you figure that out.